Let me just briefly remind you of like, this story of like applications and hardness and worst case hardness from last time when we talked about cryptography, which is sort of exactly on this subject. So I won't dwell on it too much, but remember there, one canonical assumption that you could make is this assumption that one-way functions exist. This is stronger than p does not equal np. And if you make that assumption, then by reductions, you can get to this world of mini-crypt where a lot of cryptographic primitives exist, like symmetric key encryption, digital signatures, and so forth. We also talked that by like making another minimal assumption, such as this very nice one called hardness of the learning with errors problem, you can get to cryptomania. This is a world where lots and lots of cryptographic things exist, like public key encryption, fully homomorphic encryption, all sorts of cool stuff. And one nice thing we saw there is you can actually, it's known that you can make an assumption about the worst case hardness of some problem involving lattices, which implies this LWE. So it's kind of like a nice example of making like a more minimal assumption and still getting lots of cool, effectively hardness results, which you can then transform into cryptographic algorithms. On the subject of cryptography, before we leave it, I want to mention one more cool assumption, which is extremely interesting and the subject of a lot of current research in cryptography. It's the assumption that something called indistinguishability obfuscation, or IO, exists. And I really won't say much more about that, except it's to say that there's some cryptographic procedure that kind of obfuscates programs and has the property that, like, if you give it two programs with equal functionality, their obfuscations will be computationally hard to distinguish. Well, let me not get more into it, but like, if you make that assumption and you assume that, basically NP does not equal P, or NP is not contained in BPP, then this has been the subject of research over the last 5 years, you get to a world that's like even better than cryptomania that has been dubbed obfustopia, where you can get even more cool stuff that we didn't know how to get with just, let's say, learning with errors, like deniable encryption and non-interactive key exchange without trusted setup, blah, 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 all sorts of crypto stuff. Only downside with it is, one always tries to make minimal assumptions, or assumptions that, when you assume that a problem is hard to derive consequences, you better also put in the effort to try to disprove your assumption, to try to find algorithms for it. And this is currently a highly questionable assumption. So it's known that it holds if you have, the best thing we know is that it holds if you have three things. If LWE is true, we're very happy with that assumption. And if there's like cryptographic pseudorandom generators with a certain locality property, which I personally think is kind of fine, although it's considered less standard. And then you also need a third cryptographic assumption, like the existence of k-linear maps for k greater than or equal to 3. And this is considered, I don't want to say dubious, but like, I don't think there are a lot of people that definitely believe that this assumption is true. So extremely exciting times, actually, to figure out like if this assumption is valid or not, because if it is, oh boy, you have so much great cryptography. Okay, so let me move on from that. And actually, this does give me a nice lead into the next thing I want to talk about. So if you remember learning with errors, what was this problem? It was an assumption about the hardness of solving a certain task. The task being sort of solving noisy linear equations mod a large number q. So, we know if you you can solve a linear system modulo a prime power or a prime, no problem, using Gaussian elimination. But if there's a little bit of error in the right-hand sides, then it seems to make it very hard. What I want to tell you about now, another assumption called LPN, which stands for learning parity with noise, is actually an older assumption than LWE, a little bit motivated LWE, which is like the mod 2 version of learning with errors. So it's a bit easier to state and understand, although it doesn't have such rich consequences, as it turns out, as compared with learning with errors. So let's talk about what is this learning parities with noise problem / assumption. Okay, so it's all here on one slide. So the learning parity with noise problem with parameters n, and also a constant epsilon, which is some noise rate that's between 0 and 0.5. It goes like this. Some person, nature or some person, chooses a secret string s of n bits uniformly at random. And then in some sense, the algorithm's task is to learn what this secret n-bit string is. But you know, the algorithm cannot just say, what is the n-bit string? What it gets to do is it can request, whenever it wants, a noisy linear equation about S. Okay? It's quite similar to learning with errors. And when it says, okay, please tell me a noisy linear equation about S, it gets back something that looks like this. So this is a linear equation, and I didn't write it, but it's considered mod 2. And so it looks like a linear equation on variables x equals some number b, which is 0 or 1, mod 2. Okay, and the secret holder, when it gets a request for a noisy linear equation, picks all these coefficients, a1 through an, uniformly at random. Those are just bits, 0 or 1. And the thing is, it does not, and it gives also back b, but it does not give exactly the true answer. The true answer would be like a1 s1 plus a2 s2 plus dot 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 an plus sn. It gives that back with probability 1 minus epsilon. And with probability epsilon, it flips the answer. Okay, so basically, the learning algorithm that's trying to figure out S gets back an equation that's like a correct equation with probability 1 minus epsilon, and it's like a wrong equation with probability epsilon. Okay, and remember these A's are zeros and ones, so it's like a sum of a subset of the bits on the left-hand side. Okay, and the algorithm's task is to output S, with high probability, let's say. And this algorithm has been thought about for a while in a variety of contexts, learning theory, coding theory, and people couldn't solve it. In particular, like if, epsilon is some constant, but even a small one, like 0.0001, people did not know any polynomial time algorithm for solving this problem. And so that's the LPN assumption, that there is no polynomial time algorithm for it. So again, it's not hard to see that all these assumptions I'm going to be talking about today are like strictly stronger than p does not equal np. So they're making stronger assumptions, but hopefully from using them, you can gain stronger consequences. Okay, there's a question. Is there any insight to be gained by saying that any decision problem is an instance of I/O? For instance, any 3CNF that is unsatisfiable is the same as the constant false, but obfuscated. This observation can be used to show that, like, if you get, if you have, if I'm not mistaken, that if you have indistinguishability obfuscation and NP does not equal P, then one-way functions exist. But let me think a little bit more about what you've said. One aspect of indistinguishability obfuscation, one reason I didn't get into it too much, besides other reasons of time, is the definition is kind of subtle. Let me try to think about it, just address your question offline, because the definition is a little bit subtle. But for example, the definition doesn't really require that you don't learn something about the original program by looking at the obfuscated version of the program. It just implies that two programs with the same functionality, when you obfuscate them, and the same complexity, when you obfuscate them, they cannot be distinguished, like the same circuit size. So one example of an inefficient algorithm that achieves this indistinguishability obfuscation is, given a circuit, you find the lexicographically first other circuit that has the same size and the same input-output functionality. So this does the I/O task, but is not efficient. Okay, let me get back to learning parities with noise now. And we'll talk about that I/O later. Oh, there's another question. Is there any known slow algorithm for LPN? Yes, I will get to that in just a moment. So let me just say, what is this LPN assumption good for? It's not hard to show that you can get one-way functions from it. So that's nice, and you get to this mini crypt, and in fact, gives you very efficient symmetric key encryption. And it's sort of debatable whether you can get public key encryption from this assumption, like we know you can from learning with errors. If you're willing to still believe the assumption when epsilon is very small, like 1 over root n, Then Aleknovich in 2003 showed that you can get public key encryption, but people don't know how they feel about this like extremely low error rate. That makes the problem certainly potentially a lot easier. So it's somewhere like between like Minicrypt and learning with errors. So to answer the question, the fastest known algorithm was developed right here at CMU in 2003 by Avram Blum, Adam Kalai, and Hal Wasserman. And it's a very beautiful algorithm, actually, sometimes called clever Gaussian elimination. And it runs in time 2 to the n over log n, which looks not so impressive, because it is true that with like 2 to the n time, you can solve the problem. This is like saving a 1 over log n in the exponent, but it's the fastest algorithm we know. And for cryptographic purposes, it's actually also interesting to look at a slightly different version of the question. So this algorithm uses both this much computation time, and it requests this many 2 to the n over log n many noisy linear equations. For cryptography purposes, sometimes you want to ask a slightly subtler question. What if, like, I insist that you can only ask for poly n many noisy linear equations, which is actually sufficient for you to solve the problem in 2 to the n time, information theoretically. Then what's the fastest algorithm you can do? And there, it's known you can do 2 to the n over log n time. So really just barely faster than trivial. But this one you can do with even like a near linear number of samples. So this is all for constant epsilon. So, people have been thinking about this for a while, and these are the best algorithms. So you might argue that this is a pretty safe assumption. And maybe you can base your cryptography on it as well.